Greetings everyone. This is Srikar Babu Pilli. I am going to introduce Bootstrap approaches for AR model. So first of all, let's define time series. Time series is a set of observations YT, each being recorded at a specific index T. A sequence of dependent random variables is called time series, even if the random variables are not indexed by time. This definition also includes indexing by any ordered dimension, not just time. For example, uh, process data where the measurements are taken after every stage of production. Uh, these these observations are dependent in the sense that uh, every observation is dependent on the all the previous observations, and in the process data, every observation after each stage is dependent on all the previous stages. So many time series can be represented as linear combinations of independent random variables. Some of the examples are the autoregressive models and the moving average models. Now, autoregressive model, a time series is said to be an autoregressive model of order P if it can be represented as yt equal to mu plus theta 1 yt minus 1 plus theta 2 yt minus 2 and so on up till theta p yt minus p plus epsilon t, where p is a fixed non-negative integer and mu is said to be the mean of the time series, and theta I are the parameters of the autoregressive model, and epsilon t are IID random variables with mean 0 and variance sigma square. The autoregressive model basically assumes that the current values of the time series uh, depend linearly on its own previous uh, values, and it expresses the current value of the time series as the linear function of old previous old previous values and some random error, which are assumed to be uh, identical and independently identically distributed and independent. Now, estimation of parameters in the autoregressive model. The parameters of primary interest in an autoregressive model are the thetas, and for simplicity, let us assume the mean is 0 and we observe y1 to yn, which are dependent, and we have some initial observations y1 minus p and so on y0. Now the familiar estimators of theta are the least square estimators, which we will obtain by minimizing summation of yt minus theta 1 yt minus 1 minus theta 2 yt minus 2 and so on theta p yt minus p whole square. And if you assume beta as the vector of theta is and the beta hat as the vector of the uh, least square estimators, we can then express beta hat as Sn inverse into Sn inverse summation yt minus 1 yt and so on yt minus p yt, where Sn is a p cross p matrix whose I comma jth element is summation yt minus I yt minus j. Basically, we are doing the linear regression, fitting a linear regression model where the current value of the time series is regressed on its past values, and using the beta hat equal to x transpose x inverse into x transpose y to get to arrive at this representation. Now we have a word of caution that careless generating bootstrap samples will lead to inconsistent results. Let us see this with an example. If we assume p equal to 1 and mu equal to 0 and write theta 1 equal to theta, then we get theta hat as that given expression. Now it is very clear that it is the function of the sample mean, where the xi's are yt minus 1 yt comma yt minus 1 square. Hence, it is the function of sample mean. Hence, by taking bootstrap data IID from empirical distribution of these xi's, we can arrive at a consistent bootstrap distribution estimator for theta hat. But the problem here is that these xi's are dependent. meaning that xt and xs are dependent when t is not equal to s, and hence the bootstrap procedure will not be consistent. So a more efficient bootstrap procedure is derived using the special structure of autoregressive models. Now there are some bootstrap procedures for these autoregressive models, namely the periodogram bootstrapping and block bootstrapping. But here we will discuss about residual bootstrapping and argue that this bootstrapping is consistent. The basically the idea is the residuals rt equal to yt minus summation I equal to 1 to p theta I hat yti minus 1 t running from 1 to n have similar behavior to that of errors. So we can extend the bootstrap based on residuals to autoregressive models. So let us represent uh, the let us represent our IID. Let us represent the observations we get from empirical distribution epsilon t star IID from the empirical distribution putting mass 1 by n to RT minus R bar. The bootstrap analog of beta star, the bootstrap analog beta star of beta now is given by beta hat star equal to Sn inverse summation Yt1 star, Yt star and so on up till summation Yt minus P star, Yt star, where Sn is a P cross P matrix whose I comma jth element is given by summation Yt minus I star, Yt minus J star. And Yt star is the summation theta I hat Yt minus I star plus epsilon I star. Here the y1 minus 2p star and y minus p up to so on y minus p star are the initial bootstrap observations. Now we can estimate the distribution of beta hat minus beta by the distribution of beta hat star minus beta hat. Now we have theorem regarding the consistency of bootstrap procedure, which is proved by Bose, assuming that expectation epsilon 1 power 2 times s plus 1 is finite for some s greater than or equal to 3, and that epsilon 1 comma epsilon 1 square satisfies Cramer's condition, which states that for every c greater than 0, there exists a delta c greater than 0, such that supremum of the characteristic function of epsilon 1 comma epsilon square is less than or equal to e to the power of minus delta c. Then we will have that the supremum of h boot x minus hn x is of the order of n power minus of, almost surely, where sigma is the p cross p matrix whose I comma j element is covariance of yi comma yj by sigma square, and sigma hat is the p comma p matrix whose I comma j element is the bootstrap covariance divided by the bootstrap variance, and hn and h boot are the distribution functions of root n times sigma raised to the power minus of beta hat minus beta, and root n times sigma hat raised to the power minus of beta hat star minus beta hat. Now earlier we have assumed mu is equal to 0. Now let us see what will happen when mu is not necessarily 0 and has to be estimated by the least square estimators of mu and theta. We follow the same procedure of minimizing summation yt minus mu minus summation of theta I yt minus I whole square, and arrive at the least square estimators of mu and theta I. And the bootstrap procedure for the case mu comma 0 is now extended to this general case by using the residuals rt as yt minus mu hat minus summation theta I hat yti, and replacing yt hat plus summation theta hat yt minus I star plus epsilon I star. Kobekasda will continue from now.
So good afternoon, everyone. I will explain the bootstrap simulation part for the AR1 process. To derive a bootstrap distribution estimator for beta hat, we have to be aware that y1 to yn are dependent. A careless way of generating bootstrap data may lead to inconsistent results. The following is an example. Consider the special case of AR1 process with mean 0. Since the model has only one parameter, so the least square estimate has this closed form expression as shown in the slide. Theta hat equals to t equals to 1 to n yt minus 1 yt divided by t equal to 1 to n yt minus 1 square. So least square estimate has this closed form expression, which is a function of the mean of the xt vector, where xt is defined as yt minus 1 yt comma yt minus 1 square. So we might think that that taking bootstrap data IID from empirical distribution of x1 to xn produces a consistent bootstrap estimate for theta hat. However, as I have shown via simulation for an AR1 model with 0.5 as the parameter, the histogram of the bootstrap parameter estimate performed this way is not consistent, not centered at 0.5. Let's see how. First, I generated 1000 observations from AR1 model with 0.5 as the parameter. Then I also generated an initial observation. Then I stored the values of the xt vector as defined earlier in the rows of this M matrix, as you can see in the code. Then I performed simple random sampling with replacement from the rows of the M matrix and generated 1000 observations. And I calculated the bootstrap estimate of the parameter based on these 1000 observations. I repeated this exercise 10,000 times and I got 10,000 bootstrap estimates of these parameters. Then I plotted the histogram of these 10,000 values and found that they are not centered at 0.5. As you can see in this histogram plot, so inconsistency is obvious. Now let us look at what should be a correct way of doing the bootstrap. First, we generate 1000 observations from AR1 model with 0.5 as the parameter, and we also generate an initial observation as before. Then we find the OLS estimate of the parameters. OLS stands for ordinary least squares. Then we calculate the residuals in the residual function. Then we create the bootstrap observations BWT OBS function, which takes in the residual, the initial observation, and the OLS parameter as arguments and returns the bootstrap observations. The bootstrap observations are created by adding the residuals to the product of the OLS estimate of the parameter and the previous observations. This way we generate 10,000 bootstrap samples, each of size 1000, and then calculate the estimate of the parameter again by using OLS on each of these 10,000 samples, and then we plotted these estimates. After that, we again generated 10,000 samples, each of size 1000 from AR 0.5, and calculated the least square estimator and plotted the histogram for these 10,000 values. We see that the large probability regions coincide, so the bootstrap done this way is consistent. Thank you.
Now, let us move to a more practical aspect of our analysis, which is to know the order of the AR model. We know an AR alpha model is given by the relation yt equals to theta 1 yt minus 1 plus theta 2 yt minus 2 up to theta alpha yt minus alpha plus epsilon t, where epsilon i's are IID with mean 0 and finite variance sigma square. Remember, we put no more assumption on the distribution of the epsilon i's. Now, our task is to select an alpha from 1 to p which best describes our data. We assume p to be the largest possible value of alpha which it can take, and alpha naught be the true order of the model, that is alpha naught is the maximum of j such that theta j is not equals to 0. Generally, we get the value of p from the domain knowledge or some other sources. First, let us describe a naive way to attack this problem. Let yt star be the bootstrap data as generated before using the residual bootstrap procedure. Now, under alpha, let beta star alpha hat be the bootstrap analog of beta hat alpha. We define the bootstrap estimate of the model as the minimizer of the conditional expectation of the residual sum of squares with respect to beta hat star alpha, which is given in this equation 1. However, Shao in 1996 showed that this method is not consistent for estimating alpha naught. Therefore, we modify our procedure. The first two steps are exactly same as what we did in residual bootstrap method. Obtain the LS estimate and take the residues, then sample from the centered version and create a new data. Now, here is the catch. First, we take M, not N. We take M many of the YT stars and assume that that is our entire data, keeping the initial observations intact. And then we derive the LS estimate of that data, which is denoted by beta hat star alpha NA. Now, for the conditional expectation part, we substitute it with its Monte Carlo approximation by taking B many samples and doing the average. Let us denote gamma hat NM alpha as that. Then we minimize gamma hat NM alpha over alpha to get our estimate of the order. Now, to prove that this method is consistent, we require the following theorem. Assume that the roots of 1 plus theta 1 z plus theta 2 z square up to theta b z to the power p equals 0 have roots outside of the unit circle in Argand plane, which basically implies that our time series is stationary. And epsilon 1 is 2 times s plus 1 integrable with s greater than equals to 3. And also epsilon 1 comma epsilon 1 square follows the Cramer's condition as it was discussed before. Assuming all of this, if m tends to infinity and m over n tends to 0 as n goes to infinity, then we can show that our bootstrap selection procedure is consistent. That is, probability of alpha at nm equals alpha naught goes to 1 as n tends to infinity. But before proving this result, we would require the crucial result of Bose, which basically states that under the same conditions, the bootstrap method is the residual bootstrap method is a consistent method for approximating the distribution of the OLS estimate. Now, the entire proof is pretty long, so I have presented a sketch of it. For alpha greater than equals to 0, Shao using Bose's result showed that gamma hat nm can be written in either of these two forms, either as the RSS with respect to beta hat alpha plus sigma square alpha by m plus some small op 1 over m term, or 1 by n summation epsilon t square plus sigma square alpha by m plus some small op 1 over m term. And for alpha less than alpha naught, y showed that gamma hat nm alpha is greater than equals to the RSS with respect to beta hat alpha, and also limit of the differences of the RSS with respect to beta hat alpha and beta hat alpha naught is greater than 0 almost surely. In order to prove probability alpha at nm equals to alpha goes to 1, it is enough to prove probability alpha at nm greater than alpha naught goes to 0 and probability alpha at nm less than alpha naught goes to 0 as n tends to infinity. We start by the former one. Now, probability alpha at nm greater than alpha naught is same as probability alpha at nm greater than equals to alpha naught plus 1, since both of them are integers. Now, this implies that gamma hat evaluated at alpha at nm is less than gamma hat evaluated at alpha naught, since alpha at nm is by definition the minimizer of gamma hat. Now, using Shao's result, we can say that gamma hat nm have some closed form, some nice form, and we can put those form and compare to get that the probability of OP1 is greater than equals to some sigma square, which goes to 0 as n tends to infinity. This is clear by the definition of convergence in probability. Now, the latter case, probability alpha at nm less than alpha naught, which again equals probability alpha at nm less than equals to alpha naught minus 1. This is equals to the case that probability uh, gamma hat nm alpha at nm less than equals to gamma hat nm of alpha naught, which is basically saying that alpha hat nm is the minimizer of gamma. Now these two things implies that 1 over n summation yt minus z transpose t alpha hat beta hat nm whole square is less than equals to the RSS with respect to beta hat alpha naught plus sigma square alpha naught by m plus some small op 1 over m term. We reach this equation by using Shaw's result and Weiss result on right hand side and left hand side respectively. Now doing some algebraic manipulation, we get the last line. Just see that Shaw's and Weiss result so that you can relate. Now let xn be the difference between the RSSs and Rn be the OP1 term which was mentioned above. So it implies that Rn by m is the OP1 over m term. Then if we take lim sup on both the sides and by an application of Fatu's lemma, we can say that the lim sup of the probability is less than equals to probability xn less than equals to sigma square alpha naught by m plus Rn by m infinitely often, which equals to probability Rn greater than equals to mxn minus sigma square alpha naught infinitely often and lim inf of xn greater than 0. We can say that by using Weiss result that lim inf of the differences between the RSS is greater than 0 almost surely. Now this event actually implies that lim inf of Rn is equals to infinity, which is not possible since Rn has a subsequence going to 0 almost surely. Any any sequence which goes to 0 in probability has a subsequence going to 0 almost surely. It's a very well established fact, and this implies that lim inf of Rn is less than equals to 0 and hence lim inf of Rn equals to infinity is a set with 0 probability. Thus we have proved our result.
Hi, I am Moina. So we have seen that in the model selection process, if we directly use the residual bootstrap, I mean, suppose I have a data of n number of data, and we take n number of residual bootstrap and take n number of data points and feed the data, then we can see that the model selection is not consistent. But if we choose m number of data from the residuals, from the ECDF of the residual, where m by n goes to 0, then we have proven that the model selection method is consistent. So I will try to see that through simulation. Here I have taken a AR3 process, yt equal to 0.5 yt minus 1 minus 0.3 yt minus 2 plus 0.2 yt minus 3 plus zt. The zt is a white noise which is just standard normal distribution, and the coefficient 0.5, 0.3 and 0.2 are such that the AR3 process is stationary. I mean, it satisfies that the roots of the polynomial was already given by Saptarshi, that the roots lies outside the unit circle. Now we know that the true model is p equal to 3, and I will just check for p equal to 1, 2, 3, 4, 5. I will find that the Monte Carlo estimate of that expectation and find the p for which the value is minimum. So at first I will do I have drawn a data of size 500 from this AR3 process, where I have chosen the initial values of the process as 1, 0 and 1. So y minus 2 is 1, y minus 1 is 0 and y naught is 1, and from that I have drawn y1 to y500 using this model. And then I fitted, then as usual I fitted fitted the model and got the coefficients and found a residual, centered it with respect to its mean, And then from the ECDF, I chose 500, again, I chose 500 values, and I drawn the YT star values, and then did the usual thing. In that case, I got, and I repeated the experiment 20 times. In each of the case, for each P 1, 2, 3, 4, 5, I found the Monte Carlo estimate of that expectation by taking the residuals 1000 times and calculating the residual sum of square and taking its mean. So in that case, we can see that there is a clear decrease till p equal to 3, and for p equal to 4 and p equal to 5, we can see almost a straight line. So what is happening that if we go to detail, then we can see that for each of the 20 cases, the minimum the value of p for which the minimum is occurring is different. We can see that out of the 20 values, 9 of the times we have the minimum value comes at p equal to 4. 4 of the times we can see that the minimum value comes at p equal to 5, and 7 of the times we can see that the minimum value comes at p equal to 3. So we can see that mostly in none of the case we can find a true model correctly, because in the true model we had p equal to 3. But as we have proven the result, if we just, instead of choosing 500 bootstrap samples, if we had done if we had drawn a few number of bootstrap samples, here I have taken m equal to 25, which is approximately, here n was 500, so m is equal to 25 is approximately root approximately of order root n. So m by n, we can say that m by n goes to 0. So if we have drawn 25 bootstrap samples from the same data and repeated the experiment 20 times, and for each of the 20 iteration, we can see the following graphs. So these graphs also represents the Monte Carlo estimate of the expectation of the residual sum of square. I mean mean of the residual sum of square. Okay, and for each of the p equal to 1, p equal to 2, p equal to 3, p equal to 4, p equal to 5. So here I have taken only 25 bootstrap samples from the 500 ECDF that contains 500 residual values. So in that case, we can see that in each of the case, p equal to 3 clearly gives the minimum value in the graph. So in all the 20 iteration, we got the minimum value at p equal to 3, and we can see that this method chooses the correct model consistently. So thank you.
So after the model selection is done, we are now sure that it was actually AR3 model. Now we will do some inference. By Bose's result, we are pretty sure that the bootstrap procedure is consistent. So we did 2000 bootstrap resamples, and by the Monte Carlo approximation, we found the bias estimate, an estimate of bias and variance of the OLS estimator, which is given here. So as we can see that the bias is pretty less, very close to 0. So does the variance, which is obviously true, because beta hat OLS is a very consistent estimator of the true beta. Now we also plotted the p values as the distance from the true theta increases. Now this graph shows that as we move away from the true value of theta, the p values are decreasing very fast, and after 0.15 unit distance from the true theta, we can safely reject our hypothesis. So any theta which is 1.05 unit away from our true value will be rejected by the test.
Glad to make acquaintance with everyone. I am Rajoshi Bishyash and I will start with the moving average model. Let us divert ourselves from autoregressive model and start with the moving average model. Now, what is a moving average model? A moving average model of order Q can be represented as yt equals to mu plus epsilon t plus theta 1 epsilon t minus 1 plus dot 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 plus theta q epsilon t minus q. This means that any point in the data depends on error up to its previous Q generations. That is, for a tth variable at time t will only depend on its previous t minus q data points. Now we will try to estimate q. How will you do that? A simple approach will be the assumption that the first q values of the epsilon were all 0. That is epsilon 0 equal to epsilon minus 1 equal to dot 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 epsilon minus q plus 1 equal to 0. For the starting values, we can iterate on epsilon t as this follows. For t equal to 1 to t, where capital T is the total number of data points we have. Now our likelihood function can be represented in this form, where y is the data point and mu is the mean vector. And omega represents the variance covariance matrix of these two data points. And omega can be represented in this form, where gamma k is the covariance between yt and yt minus k. That is the lag between k time points, where k runs from 1 to q. Now, by triangular factorization of omega, because of the structure of omega, we can get that omega equal to AD A transpose, where A is a lower triangular matrix and D is a diagonal matrix. And we also have that Aij is 0 for I greater than Q plus J. Now, substituting omega as AD A transpose, we get the likelihood function in this form, and where A y tilde is basically y minus mu. So we can recursively calculate y1 tilde, y2 tilde up to yt tilde. Then the exact likelihood equation can be represented in this form, where the q is the fixed value of the model. Q is the fixed value of the model, and we are estimating the parameter theta. Now, for all values of q, we can estimate the likelihood function of theta and get the log likelihood function as log L theta. And we can measure the goodness of the model based on the AIK information criteria, that is AIC, which can be represented as 2q minus 2 log L theta, where q is the number of parameters it possesses, and the log L theta term is basically log of the likelihood function. Now, less the value of AIC, better the model is. And since we have t data points, so we have some finite values or finite number of q's, and hence we can compare all the AIC to get which one has the lower value of AIC, and hence the model. We can have our q. The optimum value of q will be achieved. Now we will start with the moving average model. For moving average model, basically we are doing a bootstrap, but not the ordinary bootstrap. Now, what is ordinary bootstrap? We basically sampling from in data points and randomly creating a sample from each of the data points, from the set of data points, and we are estimating parameters based on each such samples, and we have multiple samples, like say in such samples, and we will predict our data, our parameters, and the confidence interval based on those estimates. Now, what is the usefulness of bootstrap? The block model bootstrap addresses the problem of correlation in the data by sampling blocks of contiguous observation than the individual observation. That is, it addresses the correlation between data points rather than the identicality of independence of the data point. As since the time it is a time series data, so there is some correlation between the data point. Now, how does the moving average model work? Let us understand what is the procedure of sampling. Let us understand this procedure through an example. Say we have 8 data points, that is the original. Now, for the 8 data points, we have 1, 2, 3, 4, 5, 6, 7, and 8. Now, we have, say this is a MA1 model. So, for data point number 2, we are also selecting the data point number 1 along with it, since 1 depends on 2. Similarly, if we will select a sample of size of n by q plus 1 in this case. In this case, n is 8, that is sample size is 8, and q plus 1, that is q is the order of the moving average model, which is 1, and q plus 1 is 2. So basically, we will select 4 samples. So 4 samples are, say, selected samples are 2, 3, 6, and 7. Then along with 2, 1 will get selected, along with 3, 2 will get selected, along with 6, 5 will get selected, along with 7, 6 will get selected. So our data point for the sample 1 will be 1, 2, 2, 3, 6, 7, 5, 6. Similarly, we have n such samples. This is the procedure of sample selection in moving block model. And rest, we can procedure similar. That is, we can then calculate the likelihood function for each of the model, and then we can estimate the bootstrap estimates of the parameter, and hence we have our confidence interval and the parameter estimates. Now, why would the estimate give a proper confidence interval? Let us consider GTI equal to root T theta I hat minus theta I. Then the GTI star equal to root T theta I star, that is the bootstrap sample, minus theta I star, that is the original sample's estimate. And theta is the original value. Then using Colliers theorem, classical central limit theorem, and the Marcinko SLLN, that is the strong law of large numbers, we can show that GTI star almost surely goes to GTI. GTI are all statistics based on parameter theta I. And since GTI star almost surely goes to GTI, so the confidence based on GTI star will converge to GTI. Now, what is the usefulness of moving block bootstrap compared to the ordinary bootstrap? Ordinary bootstrap does not consider the temporal dependencies of the data, which can be acquainted with the help of the moving block bootstrap. That is, ordinary bootstrap does not account for the dependencies of the data, whereas the moving block bootstrap considers the dependencies of the data which is required in time series, whereas the ordinary bootstrap just simply assumes that all the data are independent. And hence, in such cases, moving block bootstrap is much useful compared to ordinary bootstrap. Thank you for your attention and the patience for listening up to this. I hope you have a good day. Thank you.